Hey everyone, welcome to our project, and our final presentation will be on the LADWP Supply Chain Procurement Improvement. And before I give some introduction, let's first meet the team. So here's the team, and thanks everyone for working hard on this project. All right, so the LADWP is the Los Angeles Department of Water and Power and the nation's largest municipal utility company. It serves more than 4 million residents and local businesses in the city of Los Angeles. Since it's such a large organization, it acquires about $756 million worth of supplies annually. And the LADWP is a public entity, which means that all its contracts must be out for bidding. A typical P&T contract starts when an end user starts an order, which then goes onto a lot of paperwork with the contract administrator. After that, the utility buyer needs to process the order, prepare the bid paperwork, and then obtain the approval from the executives. So I want to give some framework and motivations for this project. There are two types of purchases, spot PO and the P&T contract. Spot POs or spot orders are meant for one-time orders, and they consist of a lot less paperwork. The problem here is that end users tend to use spot orders for repeat purchases to save time, which creates a conflict of interest between the administration and end users. As mentioned before, the other types of purchases is P&T contracts, and it only requires one bid for the next 35 years. There's better pricing and more reliable supplies. So in short, the company wants to maximize the use of P&T. The problem is that we have now is we want to optimize the supply chain to save processing time and money. And our first goal here is to combine the two datasets for P&T and spot PO to predict whether or not a spot PO should have been a P&T purchase. Our second goal is to predict the item demand in the next 6 months.
We first start with two datasets, spot PO and PT contracts. We want to find a linkage between the two documents and identify what items are typical repeat purchase items and have been converted from spot PO to P&T contracts. Then, considering the limitation of memory and time, we extract a subset of spot PO and name it spot label for our training process. There are a few key columns that stand out to us for modeling. For example, the NAICS code, which records North American Industry Classification System code, and vendor, which is the name of the vendor, are intuitively important features. Here is a glance of the unique values for each column in the spot label. The large numbers of unique values make machine learning a necessary process. For the EDA, we take a look at the date column. We first extract day, month, year from the date column and perform one-hot encoding and visualization. The graphs show some interesting trends. For example, the order quantity decreases from 2019 till 2022, which may be a result of the pandemic. Then for the unit price and order quantity column, we create a new column called order price, which equals to unit price times order quantity. By visualizing the log order price versus order quantity, we notice that there are clearly outliers. Thus, we standardize the price column.
For data pre-processing, we clean the data and use normalization and one-hot encoding. For example, we remove the dollar signs and commas on the unit price for data cleaning. We convert it from a string to a float and fill in the missing values with the medians. Then we normalize the unit price. We also used one-hot encoding on organization names, vendor names, and item descriptions. We should extract some keywords from the item descriptions to use one-hot encoding. We use two ways to find keywords. Firstly, we found some patterns in many keywords placed before the first or second comma. So we use the regex to filter out. And the second method we use is NLP clustering.
Why do we use NLP? There are some really challenging issues we're faced with this data set. The most prominent one is the difficulty to identify same or similar items. Out of the 100,000 instances, we have more than 44,000 unique item descriptions. and less than half of them have a unique identifier. This is partially because the large variety of items and also partially due to the small variations in similar items. Just different users use different shorthands, put words in different orders. So, and also to make things even worse, we were only given the incomplete information since only one line of actual description was in the data set. For these reasons, it is extremely critical to identify and cluster similar items using NLP models. We had modeled both at word level and sentence level. Because we are dealing mostly with broken sentences and specialty terms, modeling at the word level didn't produce a meaningful result. The clustering was a disaster. Just when we're about to give up, we found that modeling at the sentence level produced surprisingly meaningful clusters. Pick a random spot on the top left, for example. The model successfully identified similar newspaper ads description, even when the keywords are expressed differently. This is why we feel comfortable using clustering labels in our model to replace keywords.
The first model we tried was a neural network. I used vendors, organizations, keywords, and description labels as features. The majority class in the dataset is 1, which stands for yes. The baseline training accuracy is 0.625, and the testing accuracy is 0.622. Here are the metrics I got with the neural network. Noticeably, with description labels, the training accuracy is 0.899, while the testing accuracy is only 0.554, which means it suffered from overfitting. Without description labels, the training accuracy is 0.661, and the testing accuracy is 0.651. This is only a bit better than the baseline accuracy. It makes sense since many purchases can be classified as repeat only if they meet 2 or 3 conditions. Therefore, it conforms to the structure of the decision tree.
So some features that we used were unit price, quantity, extended price, dates, vendors, organizations, keywords, and description labels. After one-hot encoding, we used about 8,000 features and about 14,000 data points. A base accuracy rate was 63.4% without any extensive feature engineering, but once we added the keywords and description labels, it went up to 73.5 and 72.7 for training and testing respectively. The model also showed 89.2% for true positive rate.
The next model that we tried is the decision tree. While keeping all the other selected features the same, I generated 3 different models. The table on the bottom right has the results for each of those scenarios. After those findings, I decided to use bootstrapping to infer results based on a smaller random sample of 800. The plot that is shown on the top right is a histogram for each of the bootstrap TPR, FPR accuracy, and precision for the model that uses the addition of the description label only. The black vertical lines show the beginning and end of the 95% confidence intervals. Depending on what we want to optimize, the model that we choose to use out of the 3 will slightly differ. The fourth model that we tried is a random forest. The features that were used are listed here along with the training and testing accuracy. We realized that the best model would be either a decision tree or a random forest. On the right, I plotted the RSE curve with the area under the curve to show the TPR versus the FPR at different classification thresholds. We know that the closer the solid red and blue lines are to the top left, the better the performance is. Based on the values, we see that the decision tree seems to be a bit better with an AUC of 0.83. For task 1, we are predicting whether each item will be a repeat item. The table on this slide summarizes the 4 different metrics we used for all 4 models. The bolded values produce the highest results, and that mainly corresponds to the decision tree. As a result, we have chosen to focus on the decision tree model for task 2.
After an item was identified as a potential PNT contract item, we need to forecast future demand. RNN LSTM model is used for this. Using historical PNT and spot order data, we can predict a possible number of orders and quantities in each order. Here, we use the number of months as a proxy for the number of orders. On the right is an example. Based on this information, a final determination can be made, which will be explained in detail in the next slide.
Now let's look at a case study of using our model. To remind everyone about the procurement process, there are two main parties. The first is the various end users who are the ones that put order requests for items and quantities. And the second party is the utility buyer and contract administrator party that handled the kind of logistics and handling of the order and contracts. Here is a diagram of the workflow after. So this is from the perspective of the contract administrator who will put in the order form into a database. The next step is that the system predicts whether or not it will be a P&T and also produces a list of similarly related items for those items wanted. In the bottom right, the next step is that we use our time series forecast in order to predict the number of orders in the next 6 months and also the number of item quantities in those 6 months. And the final step is the contract administrator will then decide whether or not it is beneficial or not, in the interest of going along with the single spot purchase order or using and creating a large P&T order for the multiple end users in a group. Here's an example of the case savings that we have in the previous slide. In this example, a 3-year contract was worth $102,000 and it was placed after 3 different spot POs. If we had used a P&T contract setup initially, we would have saved the following numbers, totaling $70,000 of savings. The rates for creating the contracts are shown below. Even though a P&T contract costs about $10,000 more than a spot PO contract, you have to keep in mind that the spot PO contract extends multiple times. The diagram on the right is something that the contract administrator would be looking at. Some special columns or columns of emphasis should be the average P&T unit price column, the average unit cost savings column, and the total savings column. And we were only able to get these columns through using our machine learning predictions.
Although our project produced good results, it's important to note that there were limitations and future work is still needed. Some additional work that we thought could be done is to factor in other variables like adding a column that shows the number of days a person needs the item by. Another potential item for future work would be to use machine learning on the last step for the process mentioned on slide 18, because it is currently a manual process. Because our project is not ready to be used in the real world right now, we would like to find a way to generalize our results. The final model chosen to be used largely depends on which metric the organization wants to optimize. It's also important to note that the items listed here do not guarantee an improvement in performance, and these are just possible opportunities.
And so for the overall impact of our project and the subset data that we studied, there are a total of around 9,000 items in about 3,000 spot orders. And this totals around approximately $95 million worth of stuff. And these contracts all qualify for P&T contracts. With a 90% true positive rate, our model would have been able to avoid about 3,000 spot purchase orders, and totaling savings would result in about $18 to $34 million worth of savings, which is dependent on the number of sequential spot orders of a particular spot purchase, and then a total price savings of around $6 million.
Yeah, that's all for the presentation. Thank you so much for your time.